right, so actually, I have a little note down here to go to this video. So you guys have heard of Punxsutawney Phil? But did you know, and I didn't know this until I looked at it a couple of years ago, but Punxsutawney Phil has a set of other groundhogs that compete with him on Groundhog Day. And one of them is Staten Island Chuck. So Monday is Groundhog's Day, which honestly, if you look at the statistics of him seeing the shadow, running underneath, let's see, the sees the shadow, run underneath, and then that means it's backwards to me. So if it's sunny, it's more, he sees the shadow and there's more, 6 more weeks of winter. Okay, you're like, really? It's sunny, you saw your shadow in 6 more weeks of winter. It's really kind of backwards, right? So I just wanted to point out that not only will Punxsutawney Phil be looking for a shadow, so also will Staten Island Chuck. Okay, so we'll see. Some would say that the groundhog's got a better sense of what the weather's going to do than the weathermen. They really got a bad deal with this East Coast storm. Yeah.
Oh, yeah.
They can't win. If they
How many inches?
overestimate,
Boston,
they get in trouble. If they
a lot.
underestimate, they get in
Something,
trouble.
I think.
I think Boston got hit, but New York didn't.
New York got about a dusting of an inch.
Yeah. Oh, well.
And they already.
But they're still freaked out about it.
I
They canceled
know.
the whole public school system like the night before.
Yeah, they
Yeah.
shut down the roads.
Well, they were conservative.
Only emergency vehicles were to be on the road. Public transportation wasn't out, cars weren't out, no taxis.
You said that New York, they wouldn't get it.
They got about an inch.
So picking up where we left off, right?
Did
We're
it
kind
mention
of,
still
we're
does?
ramping up to snow events and severe weather and all that. But in the meantime, Chapter 2 just kind of talks about energy coming from the sun. And actually, even though we count on heat, which is infrared radiation, and visible light coming from the sun, actually the sun is sending us all of this. Okay? And this chart, and I kind of call them cousins. So you've heard of gamma rays, you've heard of X-rays, you've heard of ultraviolet radiation. And actually, you should kind of start to get a sense of how I named them. Short, a little bit longer, visible light. They go in this order with regard to, these are the strongest, these are the longest. Really, they are. These are the most intense, these are the longest wavelengths. Okay, so I brought this chart the other day. No, I didn't bring this chart to you guys.
Please don't make
This
us listen to
basically
that song
is
again.
kind of a look at those cousins. The other thing, and so this is kind of a repeat slide, but the other thing I wanted to point out was this. So if you get a pair of sunglasses anymore, they're polarized. And honestly, they're polarized because of this. The slide right before this, and we covered this, but the slide right before this explains what the E and the M are. Basically, all of these cousins travel through space with a particular wavelength. If they're radio waves, it's long. If they're gamma rays, it's short. Okay? But they also have this electric and magnetic component. So when you buy polarized sunglasses, basically, they are kind of like a picket fence to filter out light, all light except for one direction. So here are a pair of picket fences. These could be your polarized sunglasses. Okay? What happens if you turn picket fence one way? Okay, so basically, this is what, if you take your pair of sunglasses and break them and line them up, okay, they basically will totally filter out. Another case in point, have you ever noticed that, let me make this, okay, case in point. I had a person in my other class who was like, oh, so like a factory can kind of throw up some of its crap in the atmosphere and it makes you a pretty sunrise or sunset? Maybe. Okay. Not necessarily. So remember, one of the things you can do for your project in here is to come up with 10 photos, 10 of your photos. And they need to each be unique for a particular event. This would be an event. Anybody ever seen these kind of rays coming out of the, kind of associated with clouds? They can also be associated with like a mountain, kind of an irregularly shaped object, like a cloud or a mountain. The sun has to be kind of low on the horizon. They're called crepuscular rays. You're like, dude, what an ugly name for that. Okay, so that would be a good thing to include in your photo project. Okay, so I actually brought this styrofoam cup for this topic. So one of the things about a styrofoam cup is if I go ahead and boil water in the microwave, is my hand going to stay nice and cool when I take it out of the microwave? Assuming my hand's not in the microwave when I have it on, right? Okay. So that actually falls under this category, that the styrofoam is a poor absorber. It's an insulator, right? It doesn't absorb and it doesn't transmit. It's like Switzerland, right? Okay. And that's kind of like the air in the Earth's atmosphere. It's kind of like, yeah, you know, energy, heat can kind of come and go. It doesn't absorb it. It kind of just, it doesn't readmit it, it doesn't transfer it on. But that's different than the geosphere, okay? The Earth's surface. Okay, the Earth's surface is like sun, go ahead. During the daytime, go ahead and fill me up, basically. And actually, we said that it's the Earth getting warm, okay? And even during the daytime, but I always think of the nighttime, after it's warm, it kind of oozes energy. Actually, that's why the layer of the Earth's surface that's closest, the troposphere, it gets cooler as you go up. So one last kind of, if you're into cute little critters, that's kind of what I think of this topic down here. Okay, so if you think of the Earth's surface as kind of a nice little radiator, okay, then think of nice fresh snow, and think of that cute little bunny basically hugging the Earth. And he's got his insulation. Snow is a pretty good insulator because it's mostly air, okay? And he's set for a little while till spring comes. So, true deal. So I've got a figure coming up to kind of show you how stuff in the Earth's atmosphere does one or two things with each of those wavelengths. Okay, gases in the atmosphere, not particulates really as much, but they can either absorb or transmit energy. Okay, we call those windows. So we say the window is closed if it doesn't allow energy to either come from the sun or go from the Earth, that the window is closed. We say it's open if it's like, yeah, okay. All right, so we said it makes a difference with regard to what energy, which cousin you're talking about, and what gas or what particles it's interacting with. So I don't know if you recognize these. These are the fingerprints of the sun and the Earth with regard to their energy curves. We call them radiation curves. Along the x-axis, we have wavelengths. We have the shortest wavelength here. We would have had X-rays or gamma rays and X-rays over here, but we start ultraviolet, visible, infrared, radio waves, microwaves, radio waves. But that's kind of the signature of those. So if we pick on nitrogen first, so along the y-axis for these is absorptivity, percent absorptivity. So notice that nitrogen, with regard to kind of these longer wavelengths, and I'm going to add to it, it's going to go away here in a minute, but when you think of infrared, what I'm hoping you start to kind of think of is heat. Ah, that reminds me. So I brought this gun today. Okay. As some of you maybe recognize, it's really kind of silly, but that red dot has nothing to do with sensing. Basically, it just says, where is this pointed? So wherever the red dot is, that's where I'm getting infrared radiation information that's being translated to a temperature. Is that not cool or right? Okay, so I can go, do you think that wall should be cooler or warmer?
Cooler.
I think it's cooler too. So this was 74-ish. Ooh, 71-ish. Oh yeah. Isn't that cool? Let's see what my temperature is. 82. I could do this all day, okay? But this actually is just kind of pointing out that one of the laws of radiation is that all objects send all sorts of information. One of them is infrared radiation. So think of infrared radiation as heat. Okay, so nitrogen, it absorbs kind of in this region. infrared radiation, heat. Picking on oxygen next, actually not just oxygen. Regular oxygen's O2, what's O3?
Ozone.
Ozone, that's right. Okay, so here actually we're showing that with regard to absorptivity, why is this significant? Why do we want this to be in place?
Because that's the ozone's work.
That's the ozone's work, that's the work of the ozone, not the dipole. We want it to absorb that particular energy from the sun, exactly. So we say the window's closed for ozone, or sorry, not the ozone, the window's closed for ultraviolet, exactly, because of ozone. I'm so good at chemistry. Okay, another, so that was regular oxygen and ozone. All right, one last thing to note. Okay, see this bit about down here, atmospheric window? Basically, with regard to water vapor, carbon dioxide, and nitrogen, I'll kind of draw it on the slide. Those gases in that particular part of infrared radiation allow the Earth to, oh gosh, just kind of do it here, to cool off. So basically, this allows the Earth to cool off, possibly. Oh, it was the last one. Windows for outgoing infrared radiation or heat are important. Okay. So this is where I need to start tomorrow with my other class. But in the meantime, you probably figured this, right? I'm going to go ahead and draw a picture here. This is my Earth. I'll go ahead and draw the, what's that? Sun, that's right. And we'll pick blue, and I'll go ahead and draw a cloud. Okay, so I bet you imagine that basically that cloud is going to redirect some of that sun's energy. So this is going to be cooler. That's all that says, right? But here's the deal. Let's go ahead and tell me what this is. It's like I'm playing that charades. What's that? It is the moon. It's supposed to be the moon. Very good. Okay, let's go ahead and draw our cloud. Okay, but one of the things that clouds can do is, and this actually, remember I talked about the oozing of energy? Oh, I just love the oozing of energy. Okay, this is the Earth cooling off at night. Clouds act like a blanket, basically. Okay, so actually they have a warming effect, just like the slide says. So clouds at night make you warmer, clouds during the day could potentially make you cooler. Okay, some of the most bitterly cold nights I can remember are nice and clear. And that's not by accident. Okay, so in case you haven't visited a greenhouse recently, okay, this is a greenhouse that's got glass on all sides. And actually the greenhouse effect I'm going to describe is like if the sun is shining in the window of your car, okay, your car can get very hot, and this is why. Basically, the orange is the sun's energy, or the light energy shining through the glass. Okay, that light energy interacts with the inside of your car or with the greenhouse, and it is converted to those red things. The stuff coming from the sun is relatively short wavelength, visible light, interacts with the inside, heats it up, and the heat actually is long wave radiation. So here's the rub. Those little red squiggles, heat, will not go like just past your glass. It's stuck there because of the glass. So it's trapped. It comes in, fine, it's converted, and it can't leave. The greenhouse effect. Okay. So if we scale that up or talk about the greenhouse effect with kind of our Earth atmosphere system, this is how it looks like. Okay, so that would be the short wave radiation. Okay, the window is open to that visible light. And one of the things we know that happens is that visible light can hit the geosphere and warms up the geosphere. It's great at absorbing that energy. Well, what the geosphere or the Earth's surface returns is that it oozes that energy. Notice it's turned from yellow to red. It's changed from short to long wave radiation. Those cute little things that look like little bugs, if you look real closely, they actually are carbon dioxide and water molecules. They're both what? Variable gases in the Earth's atmosphere. Okay, so here's how those two gas particles act like glass for a greenhouse gas. For a greenhouse. Okay, just like the glass says, nope, you could come through one way if you're short wave radiation, but if you're long wave radiation, you're not leaving. So also those gases do the same thing. Okay, say nope, you're staying here. So that's how greenhouse gases work. And carbon dioxide and water vapor are only a pair of greenhouse gases. So again, to just kind of recap, we have the shortwave radiation. Our atmosphere is totally open to it. Like, ooh, come on in. Interacts with the Earth's surface, and we're going to be talking more about this oozing energy from the top of the Earth's surface. Okay, but that long wave radiation, like, no, you're staying. Okay. So I mentioned the moon, right? So the moon, do you think it has much greenhouse gas effect going on? Mm-mm. Have you ever heard about Venus and its runaway greenhouse effect? So the thing is, if you increase the number of CO2 particles, okay, you have more of a blocking effect. And so Venus is just crazy with CO2. Basically, it's got a lot of carbon dioxide in its atmosphere, so it's got a strong runaway greenhouse effect. None of us want to be like Venus, right? So this is kind of a busy slide. It's kind of like if you're into accounting, this would be your sort of slide. If we take 100 units from the sun, an assortment of things in general can happen to those 100 units, and we've talked about some of them. Okay. For instance, we already talked about how some of that energy can be reflected back to outer space. Okay. Some of it is absorbed by the clouds. And in this scenario, about half of it gets through and is absorbed by the geosphere. Okay. So with regard to the Earth kind of cooling off, it has a couple things that can cool off. Okay. One is by conduction and convection. We kind of talked about that the other day, transferring energy from the Earth to the Earth's atmosphere. Negative -7 units, right? And it also says, by the way, 7 units then would be absorbed by the atmosphere. Another way that the Earth can cool off is something called evaporative cooling. Swamp coolers, I don't know if you've lived in the South, but here's one for you. Have you ever had wet socks or something like that, and you're like, brr, okay? Anytime you have something wet next to your skin, that liquid water is trying to become a gas. Anytime liquid water can become a gas, it takes a little bit of energy. So basically what it's doing, if you have something wet on your skin, is it's taking the thermal energy from you. And you are chilling, okay? It's like, dude, I'll take your thermal energy. I'm going to turn into a vapor, okay? And it leaves you colder. It's called evaporative cooling. So anytime we have water that's on the Earth's surface and it's going from a liquid to a gas, it has a cooling effect. So that's all that is. We'll be talking more about that later. And then this is kind of the squiggles, okay? Kind of just the radiation, we said. It can lose 114 units, it gains 94 units, okay? If you kind of add those three together, you come up with the energy losing 50 units and it gained 50 units. It's a busy slide. But kind of the bottom line up here is if you are able to track all the comings and goings, it's basically a wash. What this suggests is on a typical day, we're kind of in balance, okay, with regard to the Earth, the geosphere, the atmosphere, okay, and the energy coming from the sun, which would be a good thing. So just to kind of finish things out for this chapter, I'll kind of show you where it's not balanced. It's not fair. You know, one of the things you already knew is that near the equator it's warmer. And actually we spent a fair bit of time talking about the direct rays from the sun aren't always over the equator, are they? And we talked about the summer solstice, and they are actually, the direct rays are 23.5 degrees north latitude, Tropic of Cancer. Okay, the winter solstice, Tropic of Capricorn. Okay, but what this slide talks about is just if you look throughout the year, okay, setting kind of those variations as the Earth orbits the sun aside, really at the equator, you do get ultimately more energy throughout the year than is going out. There, I looked at this slide. This figure, I like it, but it kind of drives me nuts. So let me kind of clear up what those lines are. I was like, good heavens. I looked at it for a long time this afternoon. So what you got to do is focus on, you see this purple line up here? It's purple. So the way that works is this purple line extends down here, okay, and I'll see that orange line. I think I'll grab a blue color. Okay, this orange line extends here, and it kind of crisscrosses at 38 degrees latitude, okay, and so anything up to this line right here is actually incoming. I'll just do it this way. Incoming energy, and then I'll do the purple, and then that's actually outgoing energy. Actually, I think I did green, didn't I? And actually, the next slide, I have a figure from your textbook that does basically the same thing, but I kind of like this one. So what it's saying is that near the equator and all the way to 38 degrees latitude, where basically you're equal for a given year, of the course of the year, okay, you have more energy coming in than you have going out. So that's why you have a surplus of energy. They're about 38 then degrees latitude, you start then to get a deficit. And your deficit is the most at where Santa Claus is. So let's see if you like this one any better. It shows the same information, but very different. Okay, so the way you look at this is basically you have the equator right here, okay, 5 degrees north, 5 degrees south, 25 degrees north, 25 degrees south. We're, what, about 40 degrees or so north, okay? And so, again, the red line is the amount going in, and, sorry, the red line is the amount going out, and the yellow line is the amount coming in. So definitely have a surplus there. In the next chapter, we're going to talk about ocean currents. It's kind of neat. They're humongous. Oh my gosh. It's amazing to think of how much of the Earth's surface is covered with water. Then if you think how deep the oceans are, you're like, holy cow. Okay? And actually, one of the things, and I might say it on the next slide. Is this the last slide?
Yeah.
Okay, good.
That's the last one we have.
Okay, yeah, that would be the last one then for this chapter. One of the things we're going to learn, I think in chapter 3, if not later, is that this energy is transferred by, energy transfer, I'm just going to say by oceans. Oceans are great. It's saying, okay, you've got a surplus here, you have got a deficit there. I'm going to go ahead and relocate some of your thermal energy. Okay. Very good. Well, let's take a break and return 25 after or so. All right. Sound like a plan?